Deep learning-based recommendation systems power the personalization features in popular applications such as social media, e-commerce, and entertainment streaming. As a result, neural recommendation has become a dominant source of compute at the data center scale. In this talk, we ask systems researchers and architects to take a step back and think about how user and content information are represented. More specifically, we want to take a closer look at how treating embedding representation as a design space can lead to high performance and high accuracy neural recommendation. For example, when we take a state-of-the-art recommendation model that uses embedding tables, we get fixed algorithmic and systems characteristics. However, when we consider other representations, we get to explore a wider range of trade-offs. To fully exploit this trade-off space, we first propose a new hybrid representation that uses both memory and compute resources to generate high-quality embeddings. Second, to better exploit the different systems requirements of different representations, we evaluate the accelerator compatibility of GPUs, TPUs, and IPUs. Finally, we propose multi-path recommendation execution that considers heterogeneity at the representation and hardware levels. MP-Rec exploits the mapping possibilities between representations and systems platforms by dynamically activating execution paths based on input query information. By doing so, MP-Rec ensures that users can receive the highest quality recommendations under great system performance. To learn more about MP-Rec and how it optimizes neural recommendation inference, please come to our talk on Wednesday afternoon.
We present Sigma that compiles Einstein summation expressions to locality-aware data flow. A reconfigurable data flow architecture, also known as RDA, contains vector compute, vector memory, vector file fields, and pipeline registers. Current RDA compilers utilize bandwidth from large memories such as DRAMs and vector memories with small bandwidth. In these RDA languages, data transfers between DRAM and vector memories are explicit. In contrast, we propose Sigma that utilizes bandwidth from small memories with large bandwidth. In Sigma, data transfers between vector memories, vector FIFOs, and pipeline registers are treated as first-class citizens. We evaluated Sigma by generating mappings targeting plasticine RDA and compare it against a baseline system using Tesla V100 GPU programmed by PyTorch and cuDNN. We evaluate these two systems on a wide range of different applications that could contain complex data flow or high-dimension tensor operations. Overall, we find that the combination of Sigma and plasticine delivers over 5.4x speedup over V100.
Hello everyone, my name is Jack Milchard, and I'll be presenting on APEX, a framework for automated processing element design space exploration using frequent subgraph analysis. The architecture of a processing element has a direct and significant effect on the power, performance, and area of a hardware accelerator. However, the design space of processing elements is quite large. You can have a different number and type of operation within your PE. You can change how those operations are connected within the PE. You can change how those PEs are connected to each other or an interconnect. The question we want to answer with APEX is how can we automatically generate an optimized processing element architecture for an application or an application domain. So in APEX we present automated PE specialization, which starts by analyzing application domain benchmarks to find potential optimizations using frequent subgraph analysis. This will pick out the common computational blocks within your applications. Next, the framework creates PE designs that automatically explore the design space by merging frequent subgraphs together. Finally, it automatically generates a full accelerator and its compiler using an agile hardware flow. This allows us to evaluate many different PE designs. If you're interested, please come see my talk.
Hello, I'm Griffin Burlstein, and today I'm going to very quickly tell you about a tool we made called CIDR. At a broad level, there are two real ways we can think about designing a hardware accelerator. If we happen to be a hardware design expert, we can use a hardware design language and write the accelerator directly. If not, we might use a higher level accelerator design language to express the computation we want and let that compiler toolchain turn it into an accelerator directly. Unfortunately, regardless of which approach we take to design it, debugging our hardware accelerator is going to look pretty similar. The predominant debugging tool we have is a waveform debugger, which shows every single signal at every point during the program execution, and is generally quite hard to make sense of, particularly if we're not an expert in hardware design. To help resolve this, our tool called Cider, which you're seeing on screen right now, provides a more GDB-like debugging interface. Unlike waveform debuggers, Cider operates during the program execution rather than on a trace after the fact. Because of this, Cider is able to support both breakpoints and watch points during the program's execution, as well as mechanisms for both viewing and reinterpreting signal data. If available, Cider is also able to map the current execution point back to the source code of the accelerator design language used to generate it. Put together, this makes Cider a more accessible alternative to waveform debugging. For more details on this, please see our talk, and thank you for your time.